Welcome to the fifth lesson of strength of material. We will be discussing certain aspects of analysis of stress in this particular lesson. Now, it is expected that once this particular lesson is completed, one should be able to evaluate stresses on any plane through stress transformation equations and using Mohr circle. These aspects we have discussed in the last lesson. We will be looking into some more aspects of it. Then evaluate principal stresses and locate principal planes at a particular point on a stressed body. Also, one should be able to evaluate octahedral stresses, which we will look into as we go along in this particular lesson. Hence, the scope of this particular lesson includes the recapitulation of transformation equations which we have derived in the last lesson, recapitulation of evaluation of stresses using Mohr circle. We will be looking into some aspects of octahedral stresses. We will define octahedral plane and the stresses acting on such planes, and then we will be looking into some examples how to evaluate the stresses at a particular point on a stressed body. We have discussed in the last lesson that how to evaluate the stress on a particular plane which is inclined at an angle of theta with respect to x plane, and these we have termed as transformation equations. If we have a body which is acted on by the rectangular stress components which are sigma x, sigma y in the y direction, and the shearing stresses, we can compute stress at any plane, the normal to which is making an angle of theta with x plane, and this is what we have defined as the normal stress on this plane as sigma x dashed and the shearing stress as tau x dashed y dashed. And sigma x dashed is given as in terms of sigma x, sigma y and tau x y as sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau x y sin 2 theta, the normal stress on that x dashed plane, and tau x dashed y dashed, the shearing stress on that particular plane, is equals to minus sigma x minus sigma y by 2 sin 2 theta plus tau x y cos 2 theta, and also the normal stress in the perpendicular plane to x dash can be written as sigma x plus sigma y by 2 minus sigma x minus sigma y by 2 cos 2 theta minus tau x y sin 2 theta, and eventually we had seen that sigma x dash plus sigma y dashed is equals to sigma x plus sigma y, which gives us the first stress invariant. Thereby we had calculated the principal stresses which are the maximum normal stress, the maximum and the minimum in two different planes it acts, and the magnitudes of those principal stresses are sigma 1 is equals to sigma x plus sigma y by 2 plus square root of sigma x minus sigma y by 2 square plus tau x y square, and sigma 2, the minimum principal stress, is equals to sigma x plus sigma y by 2 minus square root of sigma x minus sigma y by 2 square plus tau x y square. And the plane which gives us the maximum normal stress or the principal stresses can be evaluated through this equation, where tan 2 theta p is equals to 2 tau x y by sigma x minus sigma y, and in the physical plane this is denoted by theta p. Also, we had evaluated the maximum shear stresses on planes, and we had observed that the maximum shear stress occurs in planes which are at an angle of 45 degree with reference to the principal planes, and the magnitude of the maximum and the minimum shear stresses are plus square root of sigma x minus sigma y by 2 square plus tau x y square, and the minimum one is minus square root of sigma x minus sigma y by 2 square plus tau x y square. This we had evaluated last time. Tau max is equals to square root of sigma x minus sigma y by 2 square plus tau x y square, and tau min is equals to minus of that quantity, and the angle which can be evaluated from the normal stresses and the shear stresses, this gives us the plane on which the shear stresses will be maximum and minimum. Also, we had looked into how to compute the stresses at any plane using the concept of Mohr circle apart from the equations of equilibrium. We had used equations of equilibrium to evaluate the stress at a particular point. Now, we will look into that what we had looked into how to evaluate stress at any point using Mohr circle of stress. Let us assume that at a particular point in a stressed body, the normal component of the stresses which are acting, the rectangular stresses are sigma x, sigma y the normal stress, tau x y the shearing stress. Now, if we like to represent them in a Mohr circle, last time we had seen that this is the sigma axis, this is the tau axis, and we can denote the center of the Mohr circle at a distance from origin, which is sigma x plus sigma y by 2, which was A. We had denoted this particular quantity as A and the average stress. This particular point on the Mohr circle denotes this plane in the physical space, which is A, and thereby this particular point represents the normal stress sigma x and the shearing stress tau x y, and this particular point represents this particular plane, plane B, where the normal stress is this, which is sigma y, and this is tau x y. Now, if we join these two lines which passes eventually through the center, and in this Mohr circle the angle between these two planes is 180 degree, which is 2 theta, and in the physical space the angle between these two planes is 90 degree, half of this particular angle, and thereby this particular point is the maximum normal stress. This is the plane where the maximum normal stress acts, this is the plane where minimum normal stress acts, and from this particular diagram we can observe that the maximum normal stress, which we generally denote as sigma 1, this is nothing but equals to the distance from the origin to the center plus the radius. So, this is sigma x plus sigma y by 2, and this is the radius, which is equals to this hypotenuse, which is this square plus this square, and this distance is sigma x minus sigma x plus sigma y by 2, and eventually this distance comes as sigma x minus sigma y by 2, and this is tau x y, and that is why sigma 1 is equals to sigma x plus sigma y by 2 plus root of sigma x minus sigma y by 2 square plus tau x y square, and this gives you the minimum principal stress, which is this distance minus the radius, which will be sigma x plus sigma y by 2 minus root of sigma x minus sigma y by 2 square plus tau x y square. Now, let us look into that given a state of stress at a particular point, how do you evaluate the stress at a particular plane by constructing the Mohr circle. Now, let us assume that we have a stressed body where the stresses at a particular point are the sigma x is the normal stress on the x plane, sigma y is the normal stress in the y plane, tau x y, this gives us the positive shear, this is in the direction of positive y axis on this plane, and this is in the direction of positive x axis in this particular plane. So, these are components sigma x, sigma y and tau x y. Now, as we had defined last time that this axis represents sigma, the normal stress axis, and the y axis represents the shearing stress axis, and we take the direction of shear stress downwards to have the compatibility of the rotational angle which is in an anticlockwise direction, which will be represented in anticlockwise direction in the Mohr circle as well. Thereby, the positive normal stress and positive shear stress on this plane sigma x and tau x y, if we represent on this Mohr's plane, which is, and let us assume that sigma x is greater than sigma y, then we have the plane which is represented by sigma x and tau x y as this particular point, where the normal stress is sigma x and the shear stress is tau x y. We can represent this particular plane on this Mohr's plane, wherein the stresses are sigma y and tau x y. Now, please note here that the shear which is acting in the positive y direction on x plane, we have considered this as positive shear, and this particular shear along with this complementary shear is causing a rotation in the anticlockwise direction, which we have denoted as positive shear in the Mohr's plane, whereas the shear which is acting in the y plane, this along with the complementary shear on the other side is causing a rotation in the clockwise direction, and based on this we are calling this as a negative shear on this Mohr's plane. And if we try to represent the normal and the shear stress on this Mohr plane, then we have positive sigma y and the negative tau x y, which represents the point B, which is for this particular plane. Now, if we join these two lines, as we have seen earlier, eventually this will pass through the center of the Mohr circle, and we have seen that the distance of the center of the Mohr circle from the tau axis is equals to sigma x plus sigma y by 2, which is the average stress. Now, taking this as center and OB or OA as radius, if we plot the circle, eventually we are going to get the Mohr circle. Please note that the Mohr circle need not be constructed geometrically. If we can represent them in this particular form, we can compute the other stresses directly from this diagram itself. Now, in this particular diagram, the maximum normal stress occurs at this particular plane and the minimum normal stress occurs in this particular plane, and this normal stress we denote as sigma 1, and this particular normal stress we denote this as sigma 2. And from plane A, if we move by angle 2 theta p, we come to the plane where the maximum principal stress is located. So, in the physical plane, if we rotate by angle theta p in the anticlockwise direction, this gives me the normal, and perpendicular to this plane is the plane where the sigma 1 acts, and that is how we decide about the planes for maximum principal stresses and correspondingly the maximum shear stress. Likewise, the maximum shear stress will occur at this particular point, which is the highest point in this circle, and this is tau max, which is eventually equals to the radius of the circle, is the radius. So, this is positive maximum shear and this is the minimum shear, which is the negative of this radius. So, this gives us the values of the maximum shear stresses. Also, please note that at this point where the maximum shear stresses occur, there will have some values of normal stress, which is in contrast to the one where we have maximum normal stresses where the shear stresses are 0. Now, if we like to evaluate the stress at a particular plane from this Mohr's diagram, so this is the plane, the normal to which is oriented at an angle of theta with x axis. Since this is the reference plane, from this particular plane we move in an anti-clockwise form in the same as that of the physical plane by an angle of 2 theta, this is 2 theta, then the point which we get on the periphery of the circle represents this particular plane, and the corresponding stresses represent the normal stress, and this represents the shearing stress. That is how we compute the stresses at any plane through the Mohr circle. Now, having looked into the aspects which we have discussed in the last lesson, the concept of the equations of transformations, the concept of the Mohr circle. Now, let us look into the questions which I had posed last time. What will be the answer for this? The first question was, what is meant by state of pure shear? Now, at a point in a stressed body, as we have seen that it is acted on by the normal stress and the shearing stresses components. Now, if in this particular point at a stressed body, if we do not have any normal stress, we have only the shear stresses, then we say that this particular point of the stressed body is subjected to the pure state of shear. Now, if we look into the Mohr's diagram corresponding to this particular state of stress, we have a stressed body in which the state of stress is in the form of shear alone, and this if we try to represent in terms of the Mohr circle, then this is our reference axis sigma and tau. On this particular plane where normal stress is 0, we have only tau positive. So, normal stress is 0, tau is positive here. So, this is the point which represents this particular plane. The perpendicular plane, which is at an angle of 90 degree, in the Mohr's plane it will be 180 degree, where again normal stress is 0 and we have negative of shear of equal amount of magnitude. So, these are the 2 points on the Mohr circle, and since sigma x and sigma y both are 0, so eventually this will be the center of the Mohr circle. So, if we draw a circle with the center of at this particular point and radius from O to A, we get the Mohr circle for this kind of stress which is acting. Now, thereby this gives us the maximum value of the normal stress, which is sigma 1, and this is the minimum value of normal stress, which is sigma 2. And please note that here the values of sigma 1 and sigma 2, which is in the opposite direction, is equals to the shearing stress tau. So, the maximum normal stress is tau, the minimum normal stress also is tau, but it is negative tau. And if we look into the plane, now this is the plane which is representing this particular phase, which is phase A. So, this is the plane which is representing this phase A, and from here the plane on which the maximum normal stress acts is at an angle of 90 degree, which is twice theta p. So, theta p in the physical plane, it will be 45 degree. So, with respect to this, if we draw a normal which is at an angle of 45 degree, the plane on which the maximum normal stress acts is this, and the maximum normal stress is equals to sigma 1, which is equals to tau, and the other normal stress sigma 2 will be acting in a plane which is perpendicular to this, but in the opposite direction, which is sigma 2 is a negative tau. So, if we have a stress representation which is like you have the stress tau here, the normal stress which is acting on this plane, which is tau here, this also represents a state of pure shear. And mind that this particular plane is at an angle of 45 degree with reference to the x plane. So, either we represent that at a point in a stressed body, the stresses are purely in the form of shear or in the form of normal stresses having magnitude as that of shear, which is normal tensile in the maximum normal stress direction and the compressive tau in the other normal direction. So, this is the state of pure shear. Now, what is the coordinate of the center of Mohr circle and what is its radius? By this time you have observed that the values of the radius and the position of the center in the Mohr circle, which we have represented now. This is sigma, this is tau, and the center is located at a distance of sigma x plus sigma y by 2, and based on this we have drawn the Mohr circle, the plane which is representing having sigma x and tau x y. Thereby this particular distance is sigma x minus sigma y by 2. So, the radius r is equals to root of sigma x minus sigma y by 2 square plus tau x y square. So, center is at a distance of sigma x plus sigma y by 2 and the radius of the circle is sigma x minus sigma y by 2 square plus tau x y square. Now, what happens if sigma x plus sigma y equals to 0 and sigma 1 is equals to sigma 2? This also we have observed that the maximum in the Mohr's plane, again this is sigma, this is tau, and if we draw the Mohr circle, the center is sigma x plus sigma y by 2, and this is sigma 1, this is sigma 2. So, if sigma x plus sigma y is equals to 0, this particular point moves to this, which is that for a state of pures here, and if sigma 1 is equals to sigma 2, that means this reduces, the circle reduces to a point, and thereby there are no shear in that particular plane. Well, having looked into the aspects which we had discussed last time and how to evaluate the stresses through equations of transformation and through the Mohr circle, let us look into some more aspects of stresses, which is known as octahedral stress. Now, to find the octahedral stress, in fact, the octahedral stresses are nothing but the stresses which act on the octahedral planes. So, we will have to know what we really mean by octahedral planes. The octahedral plane is a plane which is equally inclined to all the three principal axes of reference. This is generally termed as octahedral plane. Now, if we look into the reference plane, as I said that we have normally we are representing the stresses in terms of the rectangular stress component, which are sigma x, sigma y, tau x y, with reference to x, y and z reference axis. Now, if instead of representing in x, y and z form, if we represent a reference axis system which is denoted by the principal stresses sigma 1, sigma 2 and sigma 3, then if we have a plane which is equally inclined to this three reference axis system, then this particular plane we call as octahedral plane. And since this particular plane is equally inclined to these reference planes, the direction cosines of this particular plane on these planes n x, n y and z, they are going to be the same. So, this is what is indicated here, the for octahedral planes, which are equally inclined to the reference principal axis, they have the direction cosine values n x, n y and n z all equal. And we had seen earlier that the n x square plus n y square plus n z square, the direction cosine square of three planes is equals to 1. So, thereby it leads us to the values of n x, n y and n z as plus minus 1 by root 3 for the octahedral planes. So, this is the representation of the octahedral planes. In fact, the planes which are equally inclined with reference to the principal axis system, we get 8 such planes. So, this is representing sigma 1, this is representing sigma 2 and this is representing sigma 3. Now, we will get 8 such planes which are equally inclined to these three reference axes or three reference planes, and that is why these planes are called as octahedral planes. So, the stresses which act, the normal stress, the shearing stresses which act on these octahedral planes, we call those stresses as octahedral stresses. Now, for the computation of the octahedral stresses on octahedral plane, we use Cauchy stress formula, which we have derived already, wherein at any plane which is having outward normal n, the resulting stress in the x direction, in the y direction and the z direction can be represented in terms of the normal rectangular stress components sigma x, sigma y, sigma z, and the corresponding shearing stresses tau x y, tau y z and tau z x, and along with the direction cosines n x, n y and n z. Now, we have already seen the octahedral planes are the planes which are equally inclined to the three principal reference axes sigma 1, sigma 2, sigma 3. Thereby, if we take the stress in the sigma 1 direction, we will have only sigma 1 and the shearing stresses will be absent, because principal stress, the principal plane does not have the shearing stresses. So, if we take those components as sigma x as equals to sigma 1, sigma y is sigma 2 and sigma z is sigma 3, and the shearing stress components on this are 0, because those are the principal planes. Now, if we choose any plane having outward normal n on which the rectangular stress components are sigma 1, sigma 2, sigma 3, then correspondingly the components of the resultant stress will be r x, r y and r z, which is equals to sigma 1 times n x from Cauchy stress formula, sigma 2 times n y and sigma 3 times n z. So, in the Cauchy stress formula, we are replacing sigma x by sigma 1, sigma y by sigma 2 and sigma z by sigma 3, and the shearing stress components are 0. Hence, r x equals to sigma 1 n x, r y equals to sigma 2 n y and r z is equals to sigma 3 n z. So, the resultant stress r square in terms of the sigma 1, sigma 2, sigma 3 is equals to r x square plus r y square plus r z square, which is equals to sigma 1 square n x square, sigma 2 square n y square and sigma 3 square n z square. Now, if sigma is the normal stress and tau is the shearing stress on this particular plane, which we are defining as octahedral plane, then the normal stress sigma can be represented in terms of sigma 1, sigma 2, sigma 3 as sigma 1 n x square, sigma 2 n y square, sigma 3 n z square. This we compute writing the equilibrium equations in the normal direction as we have done in the previous cases, and tau square, the shearing stress, can be represented as r square minus sigma square, and r square being this value which is substituted, sigma square if we substitute here, and if we simplify we get an expression which is like this: n x square n y square times sigma 1 minus sigma 2 square plus n y square n z square times sigma 2 minus sigma 3 square plus n z square n x square times sigma 3 minus sigma 1 square. So, these two values sigma and tau are the stress on any plane which is at which has a normal n. Now, for octahedral planes, we have noted earlier that n x, n y, n z are of equal magnitude. N x is equals to n y is equals to n z, which is equals to plus minus 1 by root 3. So, if we substitute the value of n x, n y, n z in this expression, we can get the value of octahedral stress, the normal stress on the octahedral plane, which is equals to sigma 1 plus sigma 2 plus sigma 3 divided by 3. And likewise, the tau square is going to be equals to 1/9 of sigma 1 minus sigma 2 square plus 1/9 of sigma 2 minus sigma 3 square plus 1/9 of sigma 3 minus sigma 1 square. This is what it is. Now, the values of normal stress, the sigma octahedral on the octahedral plane having n x, n y, n z as 1 by root 3 is equals to sigma 1 plus sigma 2 plus sigma 3 by 3. And if you remember, we have defined the value of sigma 1 plus sigma 2 plus sigma 3, the sum of the normal stress components, as equals to the first invariant. So, sigma 1 plus sigma 2 plus sigma 3 is equals to I 1, the first invariant. Tau octahedral square is equals to sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square divided by 9, or 9 times tau octahedral square. If we expand these and simplify, we get in this particular form, which is twice of sigma 1 plus sigma 2 plus sigma 3 square minus 6 of sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. Now, sigma 1 plus sigma 2 plus sigma 3, as we have noted that this is the first invariant I 1, and this particular expression sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1 is known as the second invariant I 2. So, we can write down the expression for tau octahedral in terms of these two invariants I 1 and I 2, which is root 2 divided by 3 times I 1 square minus 3 I 2 to the power half. So, we get the normal stress and the shearing stress on octahedral plane. Now, if sigma 1 plus sigma 2 plus sigma 3 is equals to 0 for a particular stress conditions, then on octahedral plane we will not get any normal stress, and thereby the octahedral plane will be subjected to only shearing stress, and that is what is represented through this expression. Well, having known these transformation equations, the concept of the Mohr circle and the concept of octahedral stresses which are acting on octahedral planes, let us look into some examples. How do we compute the stresses on any plane if we know the stress at a particular point on a body through the rectangular stress components like sigma x, sigma y, tau x y in two dimensional plane. Now, this is the problem which I had posed to you last time, that state of stress at a point in a body is represented here, where we have sigma x as 20 megapascal, sigma y as 30 megapascal, and the shearing stress as 20 megapascal. Now, what we will have to do is find the normal and shear stresses acting on plane AA using transformation equations. So, we will have to find out the stress on this particular plane. Now, this particular plane is inclined to the vertical at an angle of 30 degree. So, if we take the normal to this particular plane, the normal makes an angle of 30 degree with x axis. So, if we write down the transformation equation for the evaluation of the stresses, so 2 theta is going to be equals to 60 degree. So, we have the stresses acting on a particular body at a point as sigma x as 20, sigma y as 30 and tau x y as 20 ampere. Now, we have already seen that the equations for transformations are now. So, we are interested to find out the stress at a particular plane which is at an angle of 30 degree with x axis. So, we have sigma x is equals to 20 plus 20 sigma y is equals to plus 30, tau xy is equals to plus 20, and 2 theta is equals to 60 degree. The transformation equation, as we have observed, sigma x dashed, which is at an angle of theta, which is 30 degree in this particular case, is equals to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. So, if we substitute the values of the rectangular stress component, this is equals to sigma x plus sigma y by 2, which is 20 plus 30 by 2, which is 25, plus sigma x minus sigma y by 2, which is 20 minus 30 by 2, is minus 10 by 2, cos 2 theta is cos 60 degree, plus tau xy is 20 times sin 60 degree. So, this is equals to 25 minus this is 5, cos 60 is half. So, this is 2.5 plus 20 times sin 60 is root 3 by 2. So, this gives us a value of 22.5 plus 17.32, which is equals to 39.82 MPa. So, this is the value of normal stress on this particular plane, which is inclined at an angle of 30 degree with vertical. Similarly, we can compute the value of the shear stress on that plane, which is tau x dashed y dashed, which is equals to minus sigma x minus sigma y by 2 sin 2 theta plus tau xy cos 2 theta. This is equals to minus sigma x is 20, sigma y is 30, this is divided by 2 sin 60 degree plus tau xy is 20 cos 60 degree. So, this is equals to 20 minus 30 gives minus 10 minus 5. So, this is 5 times sin 60, which is root 3 by 2 plus 20 times half, and this is equals to 4.33 plus 10. So, this gives us 14.33 MPa. So, the value of the normal stress sigma x dashed is equals to 39.82 MPa, and the value of the shear stress is equals to 14.33 MPa. So, this is the solution of this particular problem, where we are computing the normal stress and the shearing stresses. Let us look into this example problem 2, where we will have to solve this particular problem, or rather we will have to solve the problem which is represented in 1 using Mohr circle of stress. Now, in the previous problem we have used the transformation equations for the solution of the stresses at any plane. Now, we are going to evaluate the stress on any plane using the Mohr circle of stress. If we look into the state of stress which we had, if we represent that, which is sigma x is 20 MPa, sigma y is 30 MPa, and tau xy we had as 20 MPa. Now, as we had represented in a Mohr's plane, you have this is sigma axis, this is tau axis. First of all, if we locate the plane where the normal stress is 20 and the shearing stress is 20, then we go in this direction as 20 and the positive shear stress as 20. Now, this particular shear stress is positive because the shear stress on this plane and the complementary shear, they are making a rotation which is anti-clockwise in nature, which we have called as positive. So, this is 20 and this is 20. Let us represent this plane which is 90 degree with respect to this x plane. Eventually, in Mohr circle it will be 180 degree. So, we represent sigma y and then tau as negative. Tau is negative because the shearing stress on this plane is causing a rotation which is clockwise in nature, which is opposite to the one which we have considered earlier. So, this is negative tau. So, this is sigma y and this is tau xy. Now, if we join these 2 points, this particular point is eventually the center of the Mohr circle, which is equals to sigma x plus sigma y by 2, sigma x plus sigma y by 2. Now, if we plot the Mohr circle, then this is the point which is representing the x plane and this is the point which is representing this y plane, and this is the maximum normal stress which is sigma 1, this is the minimum normal stress which is sigma 2. Now, we are interested to evaluate the stress at a plane which is making an angle of 30 degree with x plane. Eventually, that will make 60 degree in the Mohr circle with respect to this. So, if we with reference to this line, say line OA, if we represent that plane which is represented by this point, let us say C, this particular angle is 60 degree. Now, here we know this magnitude, we can compute this magnitude. This is sigma x O dashed is equals to sigma x plus sigma y by 2, which is equals to 20 plus 30 by 2 is 25 MPa. Let us say this is A dashed and A. So, O A dashed eventually is equals to sigma x plus sigma y by 2 minus sigma x, which is sigma x is 20 here. So, O A dash is equals to 5 and A dash is equals to 20. So, the radius O A is equals to root of 20 square plus 5 square, which is equals to 20.62. Now, we are interested to find out the stress at this particular plane. So, if we drop a perpendicular to the sigma axis, so this will give us the value of sigma x on this plane. That is the value of normal stress. Let us call that as sigma x dashed, if we call this as x dashed plane, and this magnitude will give us tau x dash y dash. Now, if we represent this angle by theta, then theta is equals to tan inverse A dash by OA dash, and A dash being 20 and OA dash being 5. So, this is tan inverse 4, which is equals to approximately equals to 76 degree. So, if we represent this angle by alpha, then alpha is equals to 180 minus 76 minus 60, which is equals to 44 degree. OC being the radius, then the normal stress sigma x dash will be equals to the distance O dash plus the radius cos alpha. So, the sigma x dash is equals to the central distance, which is sigma x plus sigma y by 2 plus r cos alpha. R is equals to root of sigma x minus sigma y by 2 square plus tau xy square, and this is equals to 20.62 as we have seen. So, sigma x dash is equals to sigma x plus sigma y by 2, which is equals to 25 plus 20.62 cos alpha, and cos of 44 degree is 0.72. So, this is going to give us a value of 39.85 MPa, which is similar to the one which we have computed through the transformation equation. And the shearing stress on this plane tau x dash y dash from the Mohr circle, if you look into tau x dash y dash is equals to r sin alpha. This is equals to r sin alpha, which is equals to 20.62 times sin 44 degree will give a value of 0.7, which is equals to 14.43 MPa, which is similar to the one which we have computed using the transformation equation. Also, from this you can compute the maximum value of the normal stress, which is represented through this point, which is equals to sigma x plus sigma y by 2 plus r. Now, sigma x plus sigma y by 2 here is 25 and r is 20.62. So, that will give you 45.62 as sigma 1. The value of sigma 1 can be equals to 45.62, and sigma 2 is equals to sigma x plus sigma y by 2, this distance minus the radius, which is 25 minus 20.62, which is equals to 4.38. So, we get the values of maximum and the minimum normal stress, or the maximum and the minimum principal stresses, and the value of the radius will give you the maximum value of the positive and the negative shear, which is equals to 20.62 MPa. So, from the Mohr circle we can compute the stress at any plane and the principal stresses and the maximum shear stresses without even using the transformation equation, and without going for a geometrical construction of the Mohr circle. Well, I have set a few more problems for you which you can compute, which we can discuss in the next class. The state of stress at a point is shown in the figure. Determine the normal and shear stresses acting on the vertical plane using transformation equations. This is the state of stress at a point in a stressed body. You will have to evaluate the principal stress, the maximum shear stress and the associated normal stress using Mohr cycle. These are the values of the principal stresses at a particular point. You will have to evaluate the octahedral stresses. So, in this particular lesson, what we have done is we have recapitulated the aspects which we had discussed in the particular last lesson, and we have evaluated the octahedral stresses. Also, we have solved some example to demonstrate the evaluation of stresses on any plane. Now, these are the questions set for you to look into. What happens to octahedral stresses when first invariant is 0? What is the value of the shear stress where maximum normal stress occurs, and what is the value of normal stress where maximum shear stress occurs? So, these answers will be given in the next lesson. Thank you very much. Welcome to the lesson 6 of the course on strength of materials. In this particular lesson, we are going to discuss certain aspects of analysis of stress. We have already looked into certain aspects of stresses. In this particular lesson, we are going to look into some more aspects of stress analysis, and once this particular lesson is completed, one should be able to understand the concept of stresses in polar coordinate system. We will be able to understand the concept of stress for axisymmetric bodies, which eventually can be derived from this polar coordinate system of stresses, and also we will look into how to evaluate the stresses at different points. Hence, this particular lesson includes the recapitulation of the lessons which we have discussed already, evaluation of stresses in polar coordinate system, and examples for evaluation of stresses at a point in a stressed body. Now, before we go into the details of the evaluation of stresses in polar coordinate systems and others, let us look into the answers of the questions which I had posed last time. Now, the questions which were posed were: what happens to octahedral stresses when first invariant is 0? Now, let us look into if you remember that the stresses on octahedral planes which we had calculated, they are the normal stress sigma octahedral, which is equals to 1/3 of